Welcome everyone. My name is Steffen Hädrich. I'm with Active Fiber Systems, a fiber laser company based in Jena, Germany. And today I would like to present our recent results on a high average power Few-cycle laser system that we are building for ELI-ALPS in Szeged, Hungary. So as you can see, there's already quite a few number of people involved into this project, with different institutions involved in Jena, Germany, and other places in Germany as well, and also the ELI-ALPS facility itself. Active Fiber Systems is a rapidly growing company which focuses on transferring research results into reliable, commercially available laser systems. Our main markets are in fundamental science, materials processing, and life science. And today we are the technological leader for high power, ultra fast fiber laser systems. We recently moved into our new building, which you can see in the back, which has more than 1,000 square meter each of lab space and office space. Our products range from oscillator type sources that can also be used for cars or SRS to 100-watt type platforms. And if we apply coherent combination also to the multi-millijoule kilowatt level at 1 micron. And we recently launched a 2-micron Fullium platform, which is already catching up in terms of performance with the 1-micron systems. To these laser systems, we can add several add-ons. For example, we can extend the pulse duration into the Few-cycle regime and also add CEP stabilization. That's something I would like to talk about today. We can offer coherent XUV sources based on high harmonic generation. And we can also offer mid-IR sources and flexible pulse patterns that can be customized to the user needs. And finally, we can also extend the usability of our sources by using OPA. So as I said, I would like to focus on a laser system which is called the HR laser. It's the high repetition rate laser system of the ELI-ALPS facility in Szeged, Hungary. It's actually two systems, which are two of the 6 main laser systems used in the facility as driver for attosecond beamline. The HR1 has already been delivered. It has a 1 millijoule, 100 kilohertz operation. That is a 100-watt Few-cycle laser system. Will be soon upgraded in terms of CEP, and HR2, the second laser system, is planned to be installed in early 2021. The major difference between HR1 and HR2 is that HR2 has 5 times higher pulse energy, so that means 5 millijoule and 500-watt Few-cycle CEP-stable laser system. And that's the system I would like to focus on today. So here's a very systematic layout of this HR2 laser system. We start with a CEO stable oscillator. Then we have a preamplifier system, which already includes the stretcher, the pulse picking and phase shaping elements. Then the major part here is a main amplifier box, which has 16 channels, which are coherently combined to one another. And finally, they are compressed in a CPA pulse compressor and then sent into a spectral broadening and pulse compression stage. So here's a look into the lab, into this 16 main amplifier channel box. So we have 8 amplifiers on the bottom, 8 amplifiers on the top, and those 16 amplifiers are coherently combined to give the system performance, which is more than 10 millijoule at 100 kilohertz, which equals an average power above 1 kilowatt at sub 300 femtosecond pulse duration. And here you can see a long-term measurement of the average power stability of this system at these parameters. And you can see that over 9 hours, we have an excellent power stability of about 1.3% RMS. At the same time, we have also a very excellent beam pointing stability shown here on the right with 6 microradians and 12 microradians in X and Y direction respectively, also measured over this 9 hours, and a measured beam quality of M square of 1.1. So to compress the pulse in time, we apply a nonlinear compression scheme, which is based on a stretched hollow core fiber, technology that has been pioneered by Laser Laboratorium Göttingen, led by Tamás Nagy and Peter Zsimon. And we are both working together with those two from Laser Laboratorium Göttingen and Max Born Institute in Berlin on this particular technique. And the advantage here is that due to the stretching of the fiber, there is no bending, which means that the lowest propagation losses can be guaranteed even for very long fibers. And this is actually very well suited to high average powers, as you will see in the following. So in our case, we use a 6 to 8 meter long capillary with 400 micron inner diameter, which we fill with argon gas. And more specifically, we have a pressure gradient with 800 millibar at the input side and about 1.9 bar at the output side of the fiber. So this is how it looks in more detail. So the CPA part is still the same. The compression part consists of an in-coupling chamber, then the up to 8 meter long hollow core fiber, and an output chamber. And finally, we compress the pulses with chirp mirrors to finally achieve the output parameters of the system. So in the first set of experiments, we were working with a 6 meter stretched fiber. In that case, we used 580 watt, 5.8 millijoule from our CPA system. And we launched this into this 6 meter of fiber. And on the right side, you can see on the blue curve, the output power with respect to input power, and with the orange curve, the transmission efficiency with respect to input power. And you can see that if once we ramp up the input power, the transmission stays more or less the same over the whole range of operation. And finally, at the full available input power, we achieve more than 300 watt of average power at the output. And as you can see here, with a very nice beam profile as shown by this mode here measured after the fiber. So we also measured the compressed pulse duration with a D-scan, which is shown here. And this D-scan measurement actually reveals that we are just below 10 femtosecond in terms of pulse duration. So that means we have demonstrated 320 watt of average power at 100 kilohertz repetition rate and the pulse duration as short as 3 cycle already. As I said in the beginning, one of the main parameters of the system is the CEP stability. So of course, this all starts with a CEO stabilized oscillator, which we measured here. So the important curves are the orange ones. Solid curve shows the power spectral density, and the dashed dotted curves the integrated phase noise. And as you can see, the integrated phase noise is just above 100 milliradians when we integrate in a frequency range from 10 Hertz to 20 megahertz. We also implement a CP preserving pulse picking in our system that we have shown in a previous publication. And of course, we also take care that we can have the most stable system design that is possible to also benefit the CP stability. Of course, some obvious questions that also come into our mind is that how do the large stretching and compression affect the CEP stability of the system? In particular, the large grading compressor potentially can introduce CEP noise. And the other important question is, what does the coherent combination actually do to the CEP stability of the system? So, and to answer this question, we were running a first set of experiments. In this case, we investigated the CEO stability of our system. That means the oscillator runs at the full repetition rate of 80 megahertz. Is then amplified in the CPA system. In that case, we used 1 to 16 channels. At the full channel count, we have more than 1 kilowatt, actually 1.1 kilowatt of average power available. We then attenuate the beam and send it into a nonlinear pulse compression stage, which is used to pre-compress the pulses and then generate the necessary supercontinuum for the F2F interferometers. And we use 2 of those. The first one is used as an in-loop interferometer, which generates the error signal, which is then through some electronics fed back to the EOM, which is placed in the CPA system itself. And the second F2F is used as a control measurement out of loop. And this allows us to study some general noise properties of our system, and of course also the effect of the coherent combination. So here you can see a measurement of a one-channel operation of the system. On the left side, you will always see the phase noise, power spectral density or the phase noise, and then the integrated CEO noise on the right side. And as you can see here in the first measurement, we have roughly 700 milliradians of integrated phase noise. But what's important to note is that the noise mostly concentrates below 1 kilohertz, and this should be very well be stabilized with a feedback loop. So this is actually what we did. So we implemented this feedback loop and were able to completely suppress this acoustic noise below 1 kilohertz, shown here in the power spectral density, but also in the integrated phase noise here. And of course, we double check this measurement by using the out of loop F2F. And here you can see very similar power spectral densities and identical integrated phase noise. So of course, we were interested in the performance of the overall system. So we repeated this measurement with a varying number of channels. So we started with this one channel measurement that I have shown before. Then we added more channels, went to 2, 4, 8, and finally to 16. And as you can see, there's virtually no difference between those measurements except for some very fine details in the experiment. And this actually leads us to the conclusion that the coherent combination does not affect the CEP noise of the system. So this is already a very encouraging result, but of course it's more important to look at the final output of the system. And to do that at 100 kilohertz, we were using a stereo ATI phase meter. In this case, a commercially available device from Single Cycle Instruments. It's also a company based in Jena, Germany. And this device allows us to measure each and every shot of this 100 kilohertz pulse train and therefore to obtain the full information of our CEP stability. So here you can see the first measurement that we have done. So on the left side, again, the power spectral density, and on the right side, the integrated phase noise. And of course, the major difference compared to the previous measurement is that we apparently have a very high contribution of high frequency noise. So it's actually mostly dominated by this high frequency part. And we were looking into the system, what the reason for this is. And we finally identified or we investigated different system parameters and found an electronic noise source in the system. And we changed that. And as you can see with the blue curve, we significantly suppressed the high frequency part of the CEP noise, showing up here in the power spectral density, but also, of course, in the integrated phase noise. And with the first feedback test, we were again able to suppress this low frequency part of the noise, also shown here in this integrated phase noise. And here we end up with about 580 milliradians of integrated phase noise with the feedback loop active. So we're actually further improving the system. So we found another part which requires some changes. We actually were able to demonstrate sub 300 milliradians in the previous system, and we are currently investigating and converging towards the sub 300 milliradians with the HR2 laser as well. So in summary, I've shown that we already have a long-term stable 10 millijoule, 1 kilowatt, 300 femtosecond fiber CPA system, which we use as, so to say, front end for the HR2 laser system. We demonstrated spectral broadening and achieved multi-millijoule free-cycle pulses at 100 kilohertz already. We have shown that the CO stability of the 16-channel system can be demonstrated and is as low as 220 milliradians. And we are currently working on the CEP stability of the final system output, which is investigated and improved, currently standing at 580 milliradians, but we are confident that the sub 300 milliradians can be expected very soon and will also be measured very soon. And with that, I would like to thank you very much for your attention.